Okay, good morning, everyone.
Good morning, sir.
So, in today's lecture, we are going to start interfacing, right? So, we have learned both microprocessors 8085 and 8086. Okay, so let me start the recording first. So, in today's lecture, we are going to start interfacing of various components to 8086 or 8085. So, today we will be dealing with memory and input output devices. So, we will try to interface memory and input output devices to 8086. And this is more of a hardware oriented thing rather than software oriented thing. Up till now, we were understanding both of the microprocessors from the perspective of software as programmers, right? We also took into consideration some hardware points, but now onwards, few lectures from now will be dedicated to hardware, because if you purchase a chip of 8086 or 8085 from the market, it's not a complete computer system, it's just the brain of the computer, right? So you should be able to design a complete microcomputer system from a microprocessor and its peripherals that you have purchased from the market, right? So the very first thing, the very first basic minimum thing that we need to have is an externally interfaced memory. And as we know that in 8085, the structure of memory is fairly simple. It is 64 kilobytes of memory and no segments inside that are there, just a chip of 64 kilobytes memory. However, in 8086, the memory interfacing would be little more involved, because there is segmentation of memory, and the memory structure is not as simple as 8085. So in the on that note, we have taken 8086 for memory interfacing. However, for interfacing other components, other peripherals, we might take 8085 also. But today we have selected 8086 for memory interfacing. So we will interface memory as well as input output devices, and we will do programming with them, right? So programming will be a very small part, but the main focus today will be on hardware, right? So let me start by taking this very simple example. Okay, just let me open it with another viewer. Yeah, so let me start by taking this example and noting few points about interfacing of memory. So I've written some points here. Let us discuss these points first. So the memory devices that we are going to interface, or in general the peripherals that we are going to interface, will be of two types. The Those two types will be general purpose peripherals and dedicated peripherals. So general purpose peripherals means you could have a memory, you could have a display, you could have keyboard and input output ports. You might have seen various computers from various vendors. They must be having at least these many things: memory, display, keyboard, and some input output ports like USB hubs, etc. Right? So these are general purpose peripherals. These are general purpose peripherals. And similarly, dedicated to one processor, there could be some special peripherals like PIC, which is programmable interrupt controller, DMA, which is direct memory access, CRT controller is also there, cathode ray tube controller is also there. So these are some dedicated peripherals which will be there depending upon the architecture of the microprocessor used. However, these general purpose peripherals will be independent of the architecture of microprocessor. You can buy any memory chip, you can buy any display, and you can buy any keyboard or input output port for your computer, right? It is not specific to your processor. However, this PIC, DMA, and CRT controller, which we will study in the coming lectures, they are sometimes specific to computers, so they are not generic enough, right? Then after this, we have semiconductor memory, because in today's lecture we are going to interface this semiconductor memory. So semiconductor memory will be of two types, RAM and ROM. We are already aware of what RAM and ROM is, but in RAM there are two types: static RAM and dynamic RAM, right? So static RAM is usually very costly as compared to the dynamic RAM, because static RAM is usually is usually used for making cache memory. However, dynamic RAM, on the other hand, is used for making the general RAM that we use in literal sense, right? So we will be giving more stress to static RAM, and we will touch some topics of dynamic RAM too, right? And we will see the difference in constructions, why they are there, and why dynamic RAM is cheaper as compared to static RAM, right? So one more important point is, static RAM, it does not needs a refresh cycle, right? And dynamic RAM, it will need refresh cycle. So what is this refresh cycle? We will talk about it little later. Then there is ROM. ROM are of various types. If you talk about hardware, then we will be mainly dealing with EPROM, electronically programmable ROM, right? So there could be various types, EPROM, then electronically erasable and programmable ROM, which is called as EEPROM. So there are various types of ROMs. So any ROM would be doing our work, but we will be talking about mainly EPROM, right? Now the next point is usually the memory chips, they their sizes are written in this way: 4K cross 8. What will 4K cross 8 means? It will mean that it has 4K locations. It has 4K locations of 8-bit each. Of 8-bit each, right? So every location will be of 8-bit or 1 byte, and 4K such locations are present. If you want to convert it to 2 raised to the power of something, you already know that the value of k is 2 raised to the power of 10, and the value of 4 is 2 raised to the power of 2. So 2 raised to the power of 12 such locations will be there for a 4K chip, and 8 bits are there for every location. So you can also call it as a 4K byte memory, or a 4K byte memory chip. So this is the usual notation: 4K cross 8. In this notation, the sizes of RAM and ROM that we are going to use will be specified, right? Then the next point is interfacing less memory than the full capacity. So as I have discussed earlier also, for 8086, the maximum amount of memory that we can use is 1 megabyte. 1 megabyte memory can be used. But since memory is costly, therefore it is not recommended to use the full range of memory if your work will be done in some smaller memory, right? So in that context, if you are not using the full memory space, then in that context, if you are using some smaller memory space, if you are using some smaller range of addresses to connect the externally interfaced memory, in that case, the very first point to note is that memory is used in continuous locations usually. Usually, the memory is used in continuous locations. For example, you bring 5 chips or 6 chips of memory from the market. So it is a good practice to connect them in sequential order, right? One memory, wherever it ends, you have to begin the second memory, so on and so forth. It has got certain advantages, as we will soon see when we will design hardware circuits, right? So if you do not do that, then additional hardware will be required to interface memories to your microprocessor. So that we will see when we will manufacture this microcomputer system. So that is one point. So in that thing, when you are using a smaller memory than the full capacity, if you are using it in the continuous locations, then the lower order address lines will be used as address lines, and the higher order address lines will be used as chip select for generation. So these points will be clear when we will take an example. And it is desired to use continuous locations for memory chip interfacing. This is what we have already cleared. And one more important point: when a microprocessor is reset through external pin, then the control is transferred to FFFF0H. This is also an important point that we should keep in mind. So when you restart your computers, what happens is it again starts reloading. I mean, the BIOS starts, and then the operating system starts, so on and so forth. So since after restarting, some operations have to happen in computer, so instructions for those are written somewhere. So in 8086, we are assuming that FFFF0H is the location where our operating system or operating set of instructions will be written. So after hardware reset, the computer should start executing the instructions written at this particular address. Now, where are the instructions for operating system written? They are written in RAM or ROM? Where are the operating instructions for a particular computer system written? Are they written in random access memory or read-only memory? We have discussed this earlier also. So anyone in the class? Where is the operating system written? Is it written in RAM or ROM? It is written in ROM, read-only memory, right? So it is written in read-only memory, and that is why, whenever we will try to interface the externally interfaced memory, ROM should be able to contain this address. ROM should be attached at this particular address. This should not be the beginning address of ROM or ending address of ROM. The only thing is ROM should include this address FFFF0H, right? So this we should keep in mind while designing the hardware circuits, right? So let's now take an example and see it at work. So there are various contents that I have written on this slide. We will take them one by one. So the problem is written here. The problem is written here in this line. Here we are saying interface to 4K cross 8 EPROMs. 4K cross 8 EPROMs. Okay. Right. One more thing is that whenever you will buy RAMs or ROMs for 8086, you will buy them in pairs. Can somebody tell me why? If you are buying RAM or ROMs for 8086, you have to buy them in pair. You should buy either 2 or 4 or 8 and so on and so forth, not 3, 5 or an odd number. So why do we buy them in pairs? We have already studied the reason for that. Can somebody make a guess? Okay, so the answer to this is we have studied that this RAM and ROM, whenever they are connected, they will be connected as odd and even bands, right? They will be connected as odd and even bands. So in that context, we do not take them in odd numbers. So if we take RAM, we will take 2 chips of RAM. So one RAM will become odd RAM, another RAM will become even RAM. Similar is applicable for ROMs also. So here the problem is interface to 4K cross 8 EPROMs. That means 2 ROMs we have purchased. Their size is 4K cross 8. So 4K cross 8 plus 4K cross 8, it will become 8K cross 8. So 2 ROMs, when they are combined, the total memory location will be 8K cross 8. And you already know that K is 2 raised to the power of 10 and 8 will be 2 raised to the power of 3. So a total of 2 raised to the power of 13 address lines will be required. A total of 2 raised to the power of 13 address lines will be required for 2 4K cross 8 EPROMs. Is it clear to everybody? Is this thing clear to everybody that for 2 4K cross 8 EPROMs, 2 raised to the power of 13 will be the number, and that is why 13 address lines from A0 to A12 will be required. Yes or no? Is it clear or not?
Yes, sir.
Right.
Yes, sir.
So similarly, you have got 2 ROMs and you have got 2 set of RAM chips also, and their sizes are 4K cross 8 again. So for RAM also, you will be requiring 13 address lines, and they will start from A0 to A12, right? So this is what we need to do. This is what we need to do. And we have to connect them according to our wish to the microprocessor. So now let's have a look at this particular chart. In this chart, I have written the addresses from A0 to A19 because we have the address bus whose size is 20 bits in 8086 microprocessor, and I have grouped them as a pair of 4. Every bit has been grouped as a pair of 4 because that way we will be easily able to see the hexadecimal representation, right? So now for this ROM, if you talk about this ROM, if you talk about this ROM set, you have the size is 4K cross 8, right? And you are using 2 such chips. That is why 2 raised to the power of 13 total address lines will be used, right? And let us say what is the value of 2 raised to the power of 13 in hexadecimal? So for that, I have done a small calculation here. You can see that I have written 2 raised to the power of 13 here. I mean, from A0 to A12, you can see all the bits are 1 and rest every bit is 0. Rest every bit is 0. So this will become 2 raised to the power of 13. So if you see the hexadecimal equivalent of that, this is all zeros. So this will be 0. This is 0001. So this will be 1. And rest everything is all 1. So it will be triple F, right? So 0, 1, F, F, F is there. So this is the size of two chip of ROMs that will be used, 4K cross 8, and this is your 2 raised to the power of 13. Now, when you are trying to interface the ROM, definitely I told you that FFFF0 has to be included. So FFFF0, it is near to this ending location of the memory, which is FFFF. This is the final ending location of the memory, and it is near to that location. I mean, in the important points that we have discussed, we said that ROM should always include FFFF0. So on that note, we will try to interface our ROM chip. We will try to interface our ROM chip at the very end of the system, right? And that is why, you know, FFFF would be the last location where the ROM will be interfaced, and we have to subtract 0, 1, F, F, F from that to be able to identify the initial location of ROM chips combined, right? So if you subtract from FF, FFF, 0, 1, triple F, what will you get? Last three Fs will all become 0, and because of these three Fs, and if you will subtract F and 1, that is 1 from F, then it will become E, as you can see here, and if you subtract 0 from F, it will still remain F. So FE000H, this will be the beginning location of the two ROM chips. One of the ROM chips will begin from FE000H, and after that the second ROM will begin and it will end at FFFFH. So this is how I have identified the initial location and the final location of these ROM chips, these set of ROM chips. So is this thing clear to everyone? How have I identified FFFF and FE000H, and why have I put the ROM at the end of the system? Is this thing clear to everyone? Yes or no?
Yes, sir.
Okay. So now similarly, you can also identify the starting and the ending location of 4K cross 8 RAM. Now we said that it is a good practice to apply RAM and ROM etc. in continuous set of addresses. So obviously, since you have attached ROM already and it is attached at the ending location of your memory, so you will do another thing, that is you will apply the RAM chip immediately before that. So this was the first address of your ROM, FE000H. You will subtract 1 from this and you will get FD000H. So this will be the last location of your set of RAM chips. And into that set of RAM chips, if you want to identify the first location, you again have to subtract 0, 1, triple F, because again the size of 4K cross 8 RAM is the same. So 2 raised to the power of 13 memory locations will be required. So again 0, 1, triple F will be subtracted from this FD000H and you will get FC000H. So this will be the beginning location of your RAM. So from FC000H to FD000H, two static RAMs will be attached, and after that from FE000H to FFFFH, two EPROMs will be attached. So we have fixed the address ranges. We have fixed the address ranges for our chips that we have purchased from the market, right? Now the next thing will be we have purchased the memory chips, we have identified the address locations where they are to be connected. That is okay, but is it that you will be directly connecting your address lines to the memory chips that you have purchased? The obvious answer is no, because if you see the microprocessor, you have address lines from A0 to A19, and if you see your memory chip, so one chip has a size of 4K cross 8. So how many address lines will be there? How many address lines will be there per memory chip?
2 raised to 12.
2 raised to the power of 12. That means this is not 2 raised to the power of 12. Address lines, how many address lines will be used? Total memory locations will be 2 raised to the power of 12. But to address total 2 raised to the power of 12 memory location, how many address lines are required? Only 12, not 2 raised to the power of 12. 2 raised to the power of 12 will be the complete set of memory locations. To be able to provide addresses, only 12 address lines are required for single chip, right? For a set of two chips, we will obviously have 2 raised to the power of 13 lines, right? So now you have identified the addresses, but that is not sufficient enough. You have to also connect the chips in the form of odd and even memory banks. So let me just remind you what we did in the case of odd and even memory banks. So give me a minute. Let me connect my charger because I think my laptop is discharging. Okay, so let me just give you a quick review of what we did for odd and even memory banks. Let me search the slides for that. Where have I kept those slides? Okay, so the slides for even and odd memory bank, they are here. Let us see what we have done for attaching even and odd memory. We need to remind those points so that we can keep it in mind and design our system, right? So this is something that we have done for that even and odd memory thing. We purchased. We were dealing only with these 4 address lines. We assumed that we have a microprocessor where there are only 4 address lines that are possible. That means at max it will be able to address 2 raised to the power of 4. That is 16 memory locations. So we bought a memory chip which had 16 locations, and every location was of 8 bits. And we said that we could buy a single memory chip and attach it to the microprocessor, but that will not help us because if it is to be interfaced in odd and even fashion, then you have to buy 2 separate chips. The advantage of that will be you will be able to write a complete word in one location for the case of 8086. Here, since you have got only 4 address lines and total 16 locations, so you will be able to write a complete word also because you have got 1 byte here and 1 byte here. So you have purchased, instead of buying a single memory chip, you have purchased 2 set of memory chip of half the full capacity, right? And instead of connecting all the address lines, we only connected address lines starting from A1 to A3 to one chip and A1 to A3 to another chip, right? It had total 4 address lines starting from A0 to A3, but we had left A0 and rest of the address lines were connected. A0 was connected as a select line of the even bank, and BHE bar was connected as the select line of the odd bank, right? So this is what we have done for this case, and we said that by making arrangement of this kind, we will be able to write or read a word into the memory simultaneously in one machine cycle, right? And the data bus, obviously, to the even bank, the lower order data bus will be connected, and to the odd bank, higher order data bus will be connected. Everyone remembers this? Does everyone remember this or not?
Yes, sir.
Okay, so this is what we should keep in mind, and on the similar lines, now we are going to design our system. We have identified the beginning and the ending addresses of set of chips, but we need to connect a set of chip. For example, if you are talking about ROMs only, we need to connect them in this fashion. We need to connect them in odd and even bank fashion. So let us talk about the 4 chips first. Let us place these 4 chips in this manner. Forget everything written on this slide. You have placed a ROM of 4K cross 8 size here, another ROM of 4K cross 8 size here, and similarly you have kept 2 RAM chips. And you intend to make this RAM as even RAM and you intended to make this ROM as even odd ROM, right? And you know which select signals are to be connected to that. So first of all, let us talk about the address lines. Let us talk about the address lines. So for any of the ROM, we knew that for single ROM, 2 raised to the power of 12 locations are possible, and that is why we have uh, 2 raised to the power of 12, address lines that are there in single ROM. Since 4 is 2 raised to the power of 2 and k is your 2 raised to the power of 10, so that is why you have got 2 raised to the power of 12 memory locations, and you need to connect them. So you said that for this set of ROM, 2 raised 12 address lines will be there, and for this set of ROM, 12 address lines will be there. But combinedly, if you see these ROMs, 13 address lines are required. 13 address lines are required, right? So if you talk about a single chip, out of A0 to A13, how many address lines should be connected? A0 to A12 only, because this is what we have seen in the previous example. We had 4 address lines to begin with, but to every chip we only connected 3 address lines by leaving the least significant address bit, right? So for these chips combinedly, we require 13 address lines. But since every chip has only got 12 locations, so we will be connecting A0 to A12, not A0 to A13, but A0 to A12. Sorry, not A0 to A12. We will be connecting A1 to A12 to every memory chip here, and A0 will be left. Right? So that we have connected total of 12 address lines here, and A0 is left for generating the chip select signal. Is this point understood by everyone? Why A1 to A12 address lines are connected here? Is this point understood? Yes or no? How many of you are still present? Please raise your
Yes, sir.
hands quickly. Please raise your hands quickly if you are present here. Please quickly raise your hands if you are present here. Okay, so let me just quickly see all those people who are present so that I can mark the attendance. Okay, so now address lines connection is clear to us. A1 to A12 will be connected to both of the chips, and obviously, if you want to designate this as even chip, then data lines from D0 to D7 have to be connected to this ROM, and D8 to D15 will be connected to the odd ROM. Still now we haven't declared them as odd and even ROM, but we intend to make one of the RAMs as even, so we decided that this will be even and the second one will be odd ROM, right? So if it is to be even ROM, then obviously the lower order data bus is to be connected and the higher order data bus is to be connected to the odd ROM that we intend to make. Now then this memory read signal bar, it has to be connected to this output enable pin of that. So this is an enable signal for the memory chip, so it has got not bigger meaning, it is just an enable signal, so it is connected. Now the next thing is to be able to design these chip select signals. We have to design these chip select signals to the memory chip. Now in the previous example we just saw that for the even order ROM you should be directly supplying A0 signal, and for the odd order ROM you will be supplying the BHE bar signal that was there, right? But in this case, the chip select signals will not only be generated by A0 and BHE, they will not only be generated by A0 and BHE, but they will also be generated by the remaining address lines. So we said that for a set of 2 memory chips, a total of 13 address locations will be there. So from A0 to A12, we will be using all the locations. From A0 to A12, all the locations will be used for generating the addressing logic. And we have used A1 to A12 here, and A0 remains, right? After that, A13 to A19. After that, A13 to A19, if you see, it will be used for chip select signal. it will be used for chip select signal, right? So together with A0 and BHE bar, the higher order lines which are remaining, the higher order address lines which are remaining, in this case they happen to be from A13 to A19, they will be used for generating the chip select logic together with A0 and BHE bar. So let us notice some few important points about that. Let us notice some few important points about that. So if you see this EPROM's addresses range and you only look at the address lines which are remaining, like from A13 to A19, and if you only look at these EPROMs, you will see that every address bit is 1. Every address bit is 1 for EPROM, right? Which is remaining after this A12. Every address bit is 1, whether you talk about one set of ROM or the another set of ROM. However, if you look about these two static ROMs, for the two static ROMs, the A13 bit is 0. A13 bit is 0 for both of the cases. However, this everything else is 1. Everything else is 1. So to be able to distinguish between EPROMs and SRAMs, we can use this A13th bit, which is 1 for EPROMs and it is 0 for RAMs, and rest everything happens to be 1. Rest everything happens to be 1 for both of the cases. So we need to keep this fact in mind while generating the chip select signal for even and odd banks. So together with A0 and BHE bar, these two facts are needed to be applied so that we can generate the chip select signal for both of these chips, right? So let me just summarize. Let me just summarize what we are intending to do. So suppose you want to select. Suppose you want to select an even bank. Suppose you want to select an even bank. So what should happen? Your value of A0 should be 0. The value of A0 has to be 0. And if you also want to select the odd bank together with it, if you also want to select the odd bank together with it, then what will you be doing? You will also select BHE bar. You will also select BHE bar as 0, because if BHE bar is 0, then your odd bank will also be selected. And now let us say you do not want to work with ROM, you want to work with RAM chips. If you want to work with RAM chips, then what should happen? For working with RAM chips, you should have this A13 bit as also 0. You can see it from this chart. The distinction between RAM and ROM can be done by bit number A13, because for ROMs it is 1 and for RAM it is 0. So for RAM chips, if you want to select them, you have to keep it as 0. That means A0 is 0, BHE bar is 0, as well as A13 is also 0. So if you see in this particular table, this is BHE bar, this is A0, and this is A13. So they have written it wrongly as your okay, this is A13, but if you zoom it, you will be able to see it as A13. This is written in very small font. Forget about the top line for now. This is the interpretation of the table, the bottom line, BHE bar, A0 and A13. So if all of them are 0, we intended to select the RAM chips and both of the banks should be activated. So can we see the explanation after that? Even and odd address in RAM. So the interpretation is also correct. This is what we intended to do. And if we keep all these signals as 0, this is what is happening, right? Similarly, let us look at another combination, 0, 1, 0. 0, 1, 0 means BHE bar will be 0. That means odd bank is selected. A0 is 1. That means even bank is not selected. And A13 is 0. That means you have selected RAM and not ROM, right? So you are selecting only odd bank from the random access memory. So let's see the explanation. Only odd address in RAM. So that is also true. So depending upon your A13 and BHE bar and A0, right, you will be able to decide these 8 conditions. You can verify it for yourself that these 8 conditions will be there for RAM and ROM chips, right? So this A13 has been introduced with an intent to select either RAM or ROM. So only 6 of the conditions, 6 of the useful conditions are shown here. The rest of the conditions are left. So they are not used for our purpose. They will be don't care conditions, right? So if you have 3 bits, what you can do is you can use a 3:8 decoder. You can apply this BHE bar here, you can apply this A0 here, and you can apply this A13 here. And out of that, you will be getting 8 outputs. Out of that, you will be getting 8 outputs, and those outputs will mean any one of these things that are written here, right? So instead of applying these directly to my hardware chips, I have applied them to a decoder, and decoder will have certain outputs. And this, if the zero output is activated, it will mean even and odd addresses from RAM is selected. If this two output is activated, then this 0 1 0 combination will be valid, and only odd addresses in RAM are selected. So this will simplify my hardware design. I am simply using one decoder, and I am trying to just connect the inputs, that is as A0, A13 and PHE bar. They are connected here, and corresponding meanings will be obtained at this pin. Now, to be able to generate the chip select signal for this even ROM, for even ROM, if I have to generate the chip select signal, you see that you have got a signal which is ended from 4 and 5, which is ended from 4 and 5. So 4 will be 100 and 5 will be 101. So let us see 100 and 101 combination here. In only these two combination, you can see that ROM is selected. ROM is selected. Even and odd addresses in ROM, and only even address in ROM. So if you want to select even addresses in ROM, only these two combinations are valid. However, one more combination for ROM is there, but it is for odd addresses. So if you only want to select even addresses in ROM, these two combinations are valid, and that is why 4 and 5 combination have been ended here, and they have been supplied to this even ROM as a chip select signal. Now, that is why you have connected them. Similarly, if you see 6 and 4 signal, so 4 will happen to be 100 and 6 will happen to be 110. So 100, it is even and odd addresses in ROM. Both of the addresses in ROM are activated, and 110, only odd addresses in ROM are activated. So 4 and 6, they will be ANDed, and they will be supplied as chip select signal to the odd portion of the ROM. So this is used as an activation signal here. Now, also one important point is the outputs are active low for this decoder. I mean, whenever an output is 0, other outputs, all of the outputs will be 1. So whichever output is 0, that output is activated. Right? So this is an active low output decoder. So whenever the inputs applied to this AND gate are both 0, in only that case the output of this AND gate will be 0, and 0 is used as a chip select signal, because this is an active low activation signal. You have seen a bubble here. That is why whenever the output of this AND gate will be 0, this chip will be activated, or correspondingly any of these 4 chips will be activated. So this is an active low output decoder. This we need to keep in mind, and that is how these chip select signals are generated. So similarly, talking about the random access memory section also, you have got these chip select signals which have been designed from this 2 and 0 as CS3 bar and CS4 bar from 1 and 0, and they have been supplied here, and you can read that from the table that they have been correctly connected. Address lines from A1 to A12 have been connected. So, and to enable this chip, you have got this read and write signals, memory read and memory write signals both, because this is the random access memory. For ROM, you only have got memory read signal from the microprocessor. So this is how you connect the externally interfaced memory to your ROM. And you have seen that the decoding part can be implemented by decoder. In the very next slide, we are going to see that if the RAM chips and ROM chips that we have used, they are not connected in this way. I mean, if they are not connected in the continuous memory locations, in that case, instead of decoder, you have to use additional hardware, which will make your circuit more complicated. And this will defy the very purpose of designing a microprocessor, because microprocessor was believed to be a general purpose circuit. So we do not require any additional hardware. So if you work systematically in this fashion, in that case, with minimum hardware, you will be able to connect your peripherals. But if you do not work in this continuous fashion, then in that case, you might require some additional hardware, which we are going to see in the very next slide. But up till now, if there are any doubts, you can ask. Is this clear to everyone, or there are some small doubts remaining in this? You can ask those doubts. Priyanshu Garg, please raise down your hand. And if everyone is present, please raise your hands once again so that I can see who is still there. Please quickly raise your hands so that I can see all. Okay, about 37 people, 39 people are there. Okay, you can raise down your hands. So, any doubts in this slide so far about connection of memory chips in form of odd and even order banks to 8086? Any doubt in address decoding or how these addresses are selected and which address line is to be used? I think this is fairly simple, right? So if there are no doubts, I will move on to the next slide, which is this. Now you are again trying to interface these static RAM. You are again trying to interface this static RAM to your microprocessor together with some ROM chips. But this time the size of the chips that you are using will be different for RAM and ROM. And you will notice that instead of using a decoder, you have to use various hardware circuits for generating the chip select signals. So let us read the problem first. Design an interface between 8086 CPU and two chips of 16K cross 8 EPROM. So you are having two chips of 16 cross 8 EPROM. So ROM chip 16K is the total number of memory location that one ROM chip has. So you have two such chips, that is why 32K will be the total locations that ROM chips will be consuming. So how many address lines will be used in that case?
15.
15. 15 address lines will be used, right? Because 32 is 2 raised to the power of 5, and you have got k, which is 2 raised to the power of 10. So a total of 15 address lines have to be used for a combination of two chips of 16k cross 8, right? ROMs. And similarly, you have two chips of 32k cross 8 RAMs. So you have got 32k cross 8 RAM chip, and two such chips are being used. So 64 K will be the total location. So how many address locations will be used for this? 16 address locations will be used for this. Is it or is it not? 16 address lines will be used for interfacing two RAM chips of 32k cross 8 size. Is it correct or not?
Yes, sir.
Right. So now you can see that ROM and RAM, they are of different sizes, right? This is the first point of difference from the previous example. And here they have applied a constraint. Select the starting address of EPROM suitably, means we are supposed to select the address of ROM according to us. And according to us, the only constraint is that ROM should include FFFF0 in itself, right? That is going to happen because that is where we have decided after reset the program execution should begin. That is what we have decided. So ROM will be including that address. This is a constraint which is from our side. They have a constraint which is introduced on RAM, and that is the RAM address must start from 00000H. So they have given the actual physical address that the RAM should start from 0000H. So obviously the address locations that we are going to use will not be continuous in nature, because if we want to include FFFF0 in the ROM addresses, then the ROM has to be connected to the end. We already know this from the last example. However, if you want to begin the RAM from 0000H, then it has to be connected from the beginning. So there will be definitely gap between these two RAM and ROM chips. So RAM can be connected together in continuous memory location. The two chips can be connected in continuous memory locations for odd and even bank, and they must start from 0000. However, ROM will be connected at the end portion, so there will be some gap between these two set of chips. So now let us see how to interface those chips. So can somebody just explain me this diagram for ROM, how these address lines are selected? Can somebody explain why these address lines are A1 to A14? If you have understood the previous example, this will be trivial for you to explain. So can somebody quickly give me the logic for connecting E1 to E14 address lines to this ROM chips? Take a minute, think about it, and give me an answer. Anyone in the class? Okay, Dinesh Mehra, are you there? Raise your hands if you're there, all of you. Asutosh Chaudhary. Asutosh Chaudhary, are you there?
Yes, sir.
Please tell me why have we connected these address lines A1 to A14 here? Were you listening to the lecture that I have just given?
Yes, sir.
Then you should be easily able to explain why A1 to A14 is connected here. No answer?
No, sir.
Okay, Ankit Agrawal. Ankit Agrawal.
Yes, sir.
Can you answer this question? Why A1 to A14 has been connected to these two ROM chips? Anyone who knows the answer can answer this question. There will be some special internal marks for answering this question. So someone who wants to answer this?
So was it because that there are 16, so we would be using 15 and 1 to 14?
Please explain it again. Explain it such that we will be able to understand why A1 to A14 are connected. We are talking about ROM chips. Manaswini.
Yes, sir. Sir,
Yes.
it's also written here that the two chips of 16K into 8. So, sir, we would be using only 15.
15, why 15?
So we won't be using the last one.
16. How did you arrive at this number 15? That's what I wanted to know. Is it because 16 is written here or is it something else?
Sir, sir, I am not able to explain it properly, but because it's given that 16K into 8 ROM, that is odd ones, so we would be using only 15. We would not consider.
How did you arrive at 15? How did you arrive at this number 15? That's what I wanted to ask.
Sir, may I try?
Sir,
Yeah. Who's that? Whose voice was the second voice?
Sir, Abhishek.
Abhishek. Yeah. Please answer that question.
Sir, actually we require two ROM of 16K into 8 and 16 into 2 means 32 and we have K means 2 raised to power 10 and 32 is 2 raised to power 5, so totally 2 raised to power 15.
Yes.
And due to this we require 15 address line from A0 to A15, 14. But in case of our arranging odd bank and event bank, we keep reserve A0 for their selection. So we use A1 to A14.
Perfect explanation. ठीक है. Your name is Abhishek Kumar, right?
Yes, sir.
Okay. The explanation is very simple. For those who have not understood it and for those who are sleeping, please understand this again. You have got ROM chips, right? Two ROM chips are there. They are saying that design an interface between 8086 CPU and 2 chips of 16 cross 8 EPROM. So there are 2 chips of 16 cross 8. Now what does that mean? 16K cross 8 means 2 chips are there, so 32K cross 8 will be there, because 16 cross 16 will make 32K addresses, and 32 means 2 raised to the power of 5. So 2 raised to the power of 5 is 32, and K already is 2 raised to the power of 10. So total will be 2 raised to the power of 15. That means 15 total address lines will be required. 15 total address lines will be required for a set of 2 ROM chips. For a set of 2 ROM chips, 15 total address lines will be required. However, as we saw in one of the previous lectures, in this example, that if we had total 4 address lines, then 3 address lines will be connected to the even and odd bank, and A0 will be remaining. It will not be connected to any of the banks, and it will be used as a select line for even order bank. So on the same note, on the same grounds, since we have got 2 raised to the power of 15 lines for a combined set of these 2 chips, we will only be using only 14 out of them, excluding A0. So you can see A1 to A14 address lines have been connected to both of the chips, and A0 will be used in the address generation logic. Is it now clear to everyone? Is it now clear to everyone?
Yes, sir.
Yes, sir.
Right.
Yes, sir.
So in this way, address lines are to be connected. Similarly, now can somebody explain why A1 to A15 have been connected here, apart from Abhishek and Manaswini? Why A1 to A15 lines have been connected for RAM chips? Can someone explain that?
Yes, sir.
Who's that? What's your name?
Sham.
Shyam.
Yes.
Full name, please.
Sham Chandra.
Shyam Chand. Okay. So please explain this.
Sir,
Why
I have.
A1 to A15 are
Sir,
connected?
we have 2 RAM of 32K, odd and even. So 32 into 264, that is 10. 2 is to power 6, and
Hmm.
K is 2 is to power 10. So
Hmm.
total is 2 to power 16.
Hmm.
So total 16 address lines will be there.
Hmm.
Sir, address line is 16, or I have A0 is not included in that. So A1 is A1 to A15 will be connected between two.
Okay, very nice, very nice. Take it. So Shyam Chandra, right?
Yes.
Right. So this is how the address lines are connected. So if the logic for connection of address lines is understood, which is fairly simple, you can also see that for these ROM chips, only memory read signal is connected, and for RAM chips, memory read and memory write, both signals are connected. Now, the important point, or the point of difference from the previous slide, is how do you connect these chip select signals? How do you connect these chip select signals for RAM and ROM? So for that, instead of using a decoder as in earlier case, decoder could be used in earlier case because all of the memory locations were connected in the continuous form. Here, what you see is the constraint is the RAM chips have to be connected from the beginning, and the ROM chips have to be connected from the end. So if the last address is FFFFH and you are having 16K cross 8 EPROM, so that means a total of 32K cross 8 locations will be there for 2 sets. So 2 raised to the power of 15 locations have to be there. So here I have written this 2 raised to the power of 15 in binary form, and the corresponding hexadecimal representation is also there. So 07FFFF should be subtracted from this FFFF. You will get this location FF000. So in these ranges, your ROM will be connected. In these ranges, your ROM will be connected. However, to be able to connect in these ranges, ROM will be connected. And if you want to connect the RAM, you have to use initial location as 0000. So the last location that you want to have can be obtained after taking the hexadecimal equivalent of 2 raised to the power of how much? 32K cross 8 chip is there, and 2 such chips is there. That is why 64K cross 8 chips are there, and 64K will mean simply 2 raised to the power of 16. So 16 bits are 1 here. You can see that from A0 to A15, all of them are ones, and the hexadecimal equivalent is 0 triple F. So to 0000, which is the beginning location, you have to add 0 triple F. So you will get 0 4 times F, and this will be the last address of RAM, right? So between that, you can see that there is a huge gap. Now, if you want to make the chip select signal, obviously A0 and BHE bar will be used. A0 and BHE bar will be used. But then for the RAM chips, a different set of address lines is used. For the ROM chips, a different set of address lines is used. So that is how the decoder cannot be used here for generating these chip select signals. Decoder cannot be used here for generating the chip select signals. So you have got these AND gates. You have got this various NAND gates and AND gates assembly of that, and that is used for generating the chip select logic, right? So let us talk only about ROM first. Let us talk only about ROM first. In ROM, how many address lines were to be used? 2 raised to the power of 15 total locations were there. So only 15 address lines were to be used. That means A0 to A14. From A0 to A14 were busy in address generation logic, right? And rest all bits, if you see, they were all ones. From A15 to A19. From A15 to A19, all of them could be used as one for selecting the two set of EPROMs. So here I have connected a NAND gate, and A15 to A19 are all connected. These address lines are all connected, and I have got a signal C, which will be used as an activator signal for the ROM chips, right? But now, you don't have to only activate ROM chips at one time. You have to activate either the odd portion of it or the even portion of it, or both of the portions, have to be used, right? So now you again see the same thing for the set of RAM chips. In the set of RAM chips, instead of using 15 lines, we were using 16 address lines. So from A0 to A15, we were using all of them. From A0 to A15, we were using all of them, and rest bits were all zeros. So you can see that from A16 to A19, we have made another set of NAND gate, but the inputs are inverted. So this will be C complement. And mind you, this C complement is not the complement of the C signal. These are just different notations. C and C complement does not mean that these are complementary signals. These are just names. It should have been written as something else, but the maker of this diagram, he put it as C complement. But the point to note here is that C complement and C are not complements of each other. They are just two signals. So by using these two NAND gates, please switch off your mics. Someone's voice is interfering. So these two signals, C complement and C, they are used as an activator signal. They are used as a part of the activator signal for RAMs and ROMs by seeing the higher order address bits, which are not used for address generation logic. Right now, let us talk about this ROM chip only. For the ROM chip, we have this one NAND gate, and apart from that, we also need this BHE bar and A0 signal. We also need this BHE bar and A0 signal. So if you see this CS2 signal or CS1 signal which is attached here, let us see this CS1 bar signal here, how it is generated. So the C signal that you have got from here is appended into the input of NAND gate together with this BHE bar, and this is used as an activator for odd bank. And similarly, if you see this CS2 signal here, the C signal, which is the activator signal for any one of these two ROMs, is used as an input here, and A0 signal is used for this even band. So I hope this point is also clearly understood. For even part, you will be using A0, and for odd part, you will be using this BHE bar signal together with the general activator of the ROM chips. And that is how these are connected here. Similarly, for the other signals, that is CS3 bar and the CS4 bar, you can do the interfacing with these RAM chips, right? So here you can see that because these memory locations were separated by some locations, so you could not use a general decoder. Instead, additional hardware components were to be used. So this is the disadvantage when you do not use continuous memory locations, right? So in today's lecture, we have only completed the interfacing of static RAM and ROM with the 8086 computer, and some portion is left for your dynamic RAM, as well as for your input output. So we will complete that in today's laboratory together with the experiments of that, right? So is any point remaining here? Does it need more explanation? Anyone with any doubts? So this complete attendance list that I download here is not what will be uploaded as is. Meanwhile, in the lectures, I also keep on asking to raise hands, and to only those people the attendances will be given. So if no one has other doubts, I will be closing the session. Okay.